The planet has water. The constraint is removing salt cheaply enough to move it at city scale. That is the anomaly. Earth is blue, but usable freshwater is a thin operating margin. Rivers, lakes, shallow aquifers, and pipes that fail. Even coastal cities can run short. Before sunrise, a mother lifts the last clear water from a plastic jug and hesitates before her son drinks. Globally, 2 billion people lack safe drinking water, and 3.6 billion lack safely managed sanitation. When safe water fails, the same cup used for breakfast can carry the pathogens that leave a child weak, feverish, and dehydrated by afternoon. Engineers are attacking this from 3 directions at once. Reverse osmosis plants strip salt from seawater. AI systems model demand, detect leaks, and schedule maintenance in aging networks. Atmospheric water generators pull freshwater directly from air using condensation or water-hungry sorbents. But none of that matters unless the physics, cost, and distribution all close. The real question is not whether we can make freshwater. We can. The question is why a world that can desalinate seawater, recover pressure from brine, and monitor pipes with machine learning still leaves billions without safe water. If the mechanics of the future fascinate you, subscribe to CivilizationX. Now, the balance sheet. Freshwater works like an account. Rain and snow recharge rivers and aquifers. Cities, farms, and factories withdraw from that account. Pollution can leave water physically present but functionally unusable. And demand is rising fast. Between 2 and 3 billion people already face water shortages at least 1 month each year. By 2050, the urban population facing water scarcity is projected to grow from 930 million in 2016 to 1.7 to 2.4 billion. Kaveh Madani, lead author of the UN report, put it bluntly: many regions are living beyond their hydrological means. The biggest withdrawal is not showers or sinks, it is food. Agriculture accounts for about 70% of global freshwater withdrawals. And with inefficient irrigation, up to 60% of that water can be lost before crops use it. So the water crisis is also a farming systems crisis. Sensors, forecasting models, and AI-guided irrigation can reduce overwatering, time deliveries to plant demand, and cut losses upstream. Then there is desalination. Reverse osmosis pushes seawater against a membrane dense enough to reject more than 99.7% of salt. That takes pressure, which takes energy. But modern plants recover up to 98% of the hydraulic energy in the outgoing brine stream and can operate around 3 to 4 kilowatt-hours per cubic meter. Industry projections suggest desalination costs could fall by up to 50% by 2030, with seawater water cost approaching about 50 cents to $1 per cubic meter in some settings. But here is the counterintuitive part. We are not only short of water at the source, we also lose a global average of about 30% of fresh water to leaks after it has already been captured, treated, and pumped. So, AI is now being deployed inside utilities to find pressure anomalies, predict pipe failure, optimize pump schedules, and enable predictive maintenance. Some systems report 40% less unplanned pump downtime and 25% longer asset life. And there is a third source: the sky. The atmosphere holds roughly 13,000 cubic kilometers of water. Atmospheric water generation can condense humidity with refrigeration, or use desiccant materials that still work down to about 20% relative humidity. But solving one problem creates another. Desalination leaves concentrated brine. Brine management now includes deep-sea discharge, zero liquid discharge systems, and recovery of minerals and chemicals such as lithium and sodium hydroxide. As John Leonhardt at MIT argues, safe discharge is manageable, but recovering value from brine is better engineering. So why do 2 billion people still lack safe water? Because production is only one layer of the system. Water can be made at the coast, then lost in pipes, priced out by energy, or never reach informal settlements at all. A cheaper cubic meter at the plant does not guarantee an affordable liter at the tap. And infrastructure triage is brutal. In Wrocław, utility executive Piotr Slomiani said a network over 2,000 kilometers long cannot be thoroughly rehabilitated without almost unlimited financial resources. The next decade is likely to favor portfolios, not miracles. Use less water in agriculture. Recycle more wastewater. Deploy desalination where coastlines, energy, and demand make sense. Use AI to cut leakage before building new supply. Expand atmospheric systems where pipes never arrive. Labs are also pushing further. Evelyn Wang's group at MIT has demonstrated solar desalination concepts aimed at continuous operation with mineral recovery and minimal waste handling. The mother with the plastic jug is not living on a dry planet. She is living inside a failed system. Overdrawn aquifers, polluted supply, leaking mains, and uneven access to better tools. The engineering is real. So is the constraint. Can future city-scale water systems combine low-cost desalination, real-time AI leak control, and safe brine mineral recovery without pushing electricity use and household prices beyond what vulnerable communities can afford? That is the question CivilizationX will keep tracking. The constraint is real. The data exists. Whether the systems built around it can act on it at scale, that is the next engineering problem. Stay with CivilizationX.